All right, thanks, Avi. It's really a pleasure to be here. And this talk is about how to fool various classes of functions, and both the title and the choice of speaker are very appropriate for April Fool's Day. And what I'm going to be talking about is epsilon bias spaces for the most part. Now, I'm sure you've all seen this before, but let me just briefly recap. Epsilon bias spaces were introduced in the work of Nauer and Nauer. What they are is basically good pseudorandom generators for the parity function, right? So if you take any non-trivial parity function and you sample an input from an epsilon bias space, then the expectation is close to 0. It's less than epsilon. Okay? So we're going to say that a class of functions f is fooled by epsilon bias spaces. Oh, sorry, and I should mention that this is joint work with the living gods of pseudo-randomness, Raghu Meka, Omer Reingold, Luca, Trevisan, and Salil, Vadhan. Okay. So a class of functions is fooled by epsilon bias spaces if the expectation when you sample for any function in this class, the expectation of a function under an epsilon biased input versus the expectation under uniform input is less than epsilon, is less than delta. Okay. So now, oh, sorry, yeah, so it's delta fooled by epsilon bias spaces. So if you take your epsilon small enough, you can get the error delta also to be small, right? Okay. So now a notion that comes up very naturally when you study epsilon bias spaces is the notion of the L1 norm of a function. So what is this? Well, let's say I have a function on the Boolean hypercube plus minus 1 to r. Now I can write the Fourier expansion of this function, which is basically writing it out in the basis of parity functions, right? I can write it as summation f hat alpha chi alpha x. The L1 norm of this function is going to be defined as L1 is the summation of the absolute values of the Fourier coefficients. And actually this summation can be over just the non-trivial parity functions. I'm going to ignore this distinction throughout this talk. Okay. Now one thing which is easy to see is that if the L1 norm is small, right, let's say it's polynomial in n, then by taking epsilon to be even smaller, inverse polynomial in it. So if the L1 norm is like n, if you take epsilon to be 1 over n squared, then you'll fool this class pretty well, right? The error under any epsilon bias space can be bounded by epsilon times the L1 norm. So certainly you can fool all functions which have small L1 norm. The question is this also a necessary condition? Can you only fool things which have small L1 norm? And the answer is not quite. There is a necessary and sufficient condition, but it's not as restrictive as this. So being fooled by epsilon bias spaces is equivalent to having sandwiching approximations of small L1 norm. So what are sandwiching approximations? Let me define those. So I'm going to say that f has delta sandwiching approximations of L1 norm T if there exist two functions, f upper and f lower, such that the following things hold. Pointwise, f upper is always larger than f, it's always larger than f lower x, right? So it's sandwiched between these two functions. And the L1 norm of f upper and f lower of each of these guys is at most t, right? So what really happens here is that this upper polynomial, these two, they cannot tell the difference between truly uniform random bits and epsilon biased random bits, And your function f is kind of sandwiched between these two things. This polynomial ensures that the expectation is never too high. This polynomial ensures that the expectation is never too low, right? So if you have such sandwiching approximations, okay, sorry, what is the error of these sandwiching approximations? There's one more parameter here, which is expectation So I want these sandwiching approximations to be good approximations to you. And rather than measuring the distance from fx for each of them, I can just ask about the error between these two guys. I want that to be small, right? If I have these conditions, then any epsilon bias space will fool such an f with an error parameter which is like delta plus epsilon t. Delta prime is equal to delta plus epsilon t. Conversely, if you are able to say that any epsilon bias space fools a class of functions, then by LP duality there actually should exist such sandwiching approximators, right? So this LP duality connection was first explored in the work of Bazi, right, in proving that bounded independence fools DNFs. In the context of epsilon bias spaces, I've first seen this stated in a paper of Day et al. Right? That this similar, when you talk about bounded independence, your sandwiching approximators need to be low degree.
Properties are you requiring of the family, like that to be closed under some operation?
No, pick your favorite family of functions.
So even for a singleton, this is true?
Sure, but a singleton has these sandwiching approximators. Well,
oh, okay, fair. Okay.
I mean, I'm not sure what singleton you were talking about, but we're talking about classes like DNFs, AC0, and so on, right? If you can prove that every function in AC0 has non-trivial sandwiching approximators, then you'll get some nice pseudo-randomness for AC0. Okay. So this is the state of the art with regard to fooling classes of functions with epsilon bias spaces. In some sense, we have this clean characterization using LP duality. We have a good sense of the things that we can and cannot fool using them. I mean, obviously there are some things we still don't understand, but the focus of today's talk is not about the things that you can fool using epsilon bias spaces. It's more about things that you cannot fool using epsilon bias. So yeah. I think so, right? I mean, this is even a stronger statement. We'll actually want the strong statement because we'll end up. So tight in the sense, well, this theorem tells you these also have sandwiching approximations. And if they have sandwiching approximations, sure, they are fooled by epsilon bias spaces. What better statement could you hope for if you restrict? Yeah, so it basically the same thing holds even in the Boolean case, and I think there's not much more I don't see a way to take advantage of the Booleanness of the functions. And actually, we care about this more general statement because we'll pass to non-Boolean functions fairly often in our talk. Okay? Okay. So as I said, this talk is going to be about the kinds of things that we cannot do using just epsilon bias spaces themselves. So what are some simple classes which seem beyond the reach of epsilon bias spaces? There's read once CNFs. Well, of course, all CNFs and DNFs, but even read once CNFs and DNFs in particular, right? You know that in order to get good sandwiching approximators with error delta, you need L1 norm, which is something like n to the log 1 over delta, right? So if delta is inverse polynomial in n, this is n to this polylog n, right? So the epsilon needs to be really small. Oh, sorry, I should have mentioned in my epsilon, while talking about epsilon bias spaces, that the seed length for generating a string from an epsilon bias space is log 1 over epsilon plus log n, ignoring all kinds of constant factors, right? So as long as epsilon is inverse poly in n, this is seed length, which is just log n. But if you take something like epsilon is 1 over n to the log n, then that's a seed length of log squared. So read once CNFs, we cannot fool them using just epsilon bias spaces. Combinatorial rectangles. If you don't know what these are, I'll define these very shortly. Maybe I should define them right now. So what is a combinatorial rectangle? Well, it's a function which is an AND of coordinate functions fi, I going from 1 through m. Each coordinate function, just think of it as an arbitrary function on log n bits, and the various coordinate functions are disjoint, right? So I'm going to define fi to be a function from plus minus 1 raised to w to 0, 1. I'm going to do this switching between plus minus 1 and 0, 1 a lot in this talk, sometimes for good reasons, otherwise just for no reasons. And hopefully it won't be too distracting, right? So a combinatorial rectangle, you have these m coordinates. Each of them places some restriction on the bits that it reads, and if all these functions are satisfied, then the function is 1. Okay. So these are a class of functions that have been very well studied in derandomization by a lot of people, including Avi here. Finally, yeah. Yeah. So there are m blocks, and each of these take log n variables, let's say. So I'm going to think of two parameters, the width and the number of coordinates, that is m and w. So the total number of variables n is m times w. All right. Finally, width 3 read once branching programs. So why width 3, right? So in some sense, the holy grail of derandomizing space-bounded computation is to come up with pseudorandom generators for read once branching programs which have seed length log n, right? Nissan's generator gave us seed length of log squared n way back in 1992, and really there have been no asymptotic improvements to this except in some very restricted cases. And what we are also going to present is another small improvement in another restricted case. But for width 2 read once branching program, you can fool these by epsilon bias spaces. Width 3 you cannot. I'll show you why in a second. The best seed length we know for pseudorandom generators for width 3 is still the log squared n from Nissan. For hitting sets, you have something slightly better. You have a seed length of log n when epsilon is a constant. This is a recent work of Seema and Zach. They give a hitting set generator, what is a hitting set generator, right? If my branching program accepts with probability which is sufficiently large, then their generator can produce at least one string that it will accept. Now large in their case is really large. I think it's something like, it's some constant like 1/6, or maybe it's even greater than half, okay? So here, hitting set generator, you can get seed length log n when epsilon is a large constant. So I should also tell you what's the state of the art for these other things. For combinatorial rectangles, we know good hitting set generators with seed length log n. So this is work by Armoni, Luby, Zuckerman, and Sachs. No. Okay, so there's 3 papers. Okay, so I think if we, between all of us, I think we've said all the relevant names. So hitting set generators, you can get seed length log n even when epsilon is polynomially small. As far as PRGs go, the best result is due to Chijen Lu. It gives you seed length which is log n plus log 1 over epsilon to the 3 halves. If epsilon is polynomially small, this is a seed length of log n to the 3 halves, right? For read once DNFs, I think the best generators known have seed length something like log n times log n over delta. Is this right, Raghu? This is in the general case, and the read once case, it's log n times log 1 over delta. That's unimportant. Really, what you should take away is that when delta is small, the seed length known, the best seed length known is log squared n, even in the case of read once DNFs. Okay. And okay. Yeah. This is for regular branching programs, right? So it's a different kind of restriction. We are restricting the width here. If you just say I only care about width this, then width 2 you can fool using epsilon bias spaces. This is an old result of Sachs and Zuckerman, which I'm sure you've all seen and heard since it was never published anywhere. But, yeah, so for width 3 nothing much is known. Okay? All right. Now, so why does epsilon bias not fool any of these classes of functions? The culprit really is just the tribes function, which happens to be a common subproblem of all these classes, right? So let me define the tribes function for you. I'm going to view it as an OR of ANDs, right? So each of these is an AND of W variables. I'm going to assume the variables come in order, right? So there's x1 through xw. Then the next gate looks at xw plus 1 through x2w, and so on and so forth. The number of clauses m is going to be approximately 2 raised to w to keep the function interesting. Right? Okay. It's obviously a read once DNF. It is also a combinatorial rectangle where the functions fi are just the AND function, right? What makes it a combinatorial rectangle is that the first w variables go into the first AND gate. The next w variables go into the second, and so on and so forth. Right? And finally, it's easy to see why you can do this using a bit 3 branching program. And what we know about this function, this seemingly simple function, is that basically this L1 norm lower bound holds for this function. It holds not just if you want to compute it exactly, but even if you want to approximate it. This was again proved in this work of Day et al. Right? Now, the exact L1 norm of this function, it's actually a very nice open, not L1 norm, but how sparse is this function? This is a very nice open question. It's related to something called Mansour's conjecture, right? So there's still a lot we don't know about it, but we know that just using epsilon bias spaces and L1 norm, you will not get small seed length for this class of functions. Okay. All right. So what I'm, sorry? So for DNFs, small hitting sets are easy, right? Yeah, but for CNFs, even hitting sets are not easy. We are giving a PRG, but as far as I'm aware, this is also the first hitting set construction which works for polynomially small error. Already read once CNFs, hitting sets are not trivial, and I don't think there was anything known before our work which achieved polynomially small error. It seems like a very simple question, right? You have a read once CNF, we just want to hit it somewhere, assuming that it's read once. You hit it somewhere, assuming it has a lot of satisfying solutions. Okay. Now, what I'm going to do in this work, maybe let me write this down here. We're going to get seed length, which is basically log n over epsilon. It's O tilde log n over epsilon, which means I hide things like log log, poly, log log log, and so on and so forth. And I'm sure that you're all happy that I'm hiding these factors because it can get very ugly. But the seed length is basically, for all practical purposes, it's log n over epsilon, right? Even if epsilon is polynomially small, this is giving you a seed length which is very close to log n. Okay, and why is it so important to get good generators when epsilon is small, right? I'll talk about this in a minute. There are some reasons for it, but I think what's more interesting here is that there is a general technique for constructing pseudorandom generators where you do the following. This general technique it consists of applying mild but pseudorandom restrictions. So random restrictions are a powerful technique for dealing with things like DNF formulas, where you basically take a bunch of variables and you just set them to random values, and then the formula will simplify. What we do is that we don't apply a very harsh random restriction. We'll just set something like a constant fraction of the bits at a time, right? This doesn't do a whole lot by way of simplifying your formula, right? It simplifies it in some way, but some small way, but it doesn't really collapse it to a decision tree or anything like that. But more importantly, this can be de-randomized. We show that whether you apply these restriction bits uniformly randomly or from an epsilon bias space, the outcome is more or less the same, right? And this suggests a natural iterative procedure where you go on applying these pseudo-random restrictions till finally you've basically set almost all the bits. What you have left is some junta-like function which is very easy to fool. And I guess this idea of de-randomizing random restrictions and using it iteratively goes back to work of Aitai and Bigderson on DNF formulas from 1985. Okay. So all of them, yeah. So that's the interesting thing. It's sorry, I should say what I'm getting more clearly, right? Seed length log n over epsilon. This gives PRGs for combinatorial rectangles and read once CNF DNFs, right? For the width 3, what we get is a hitting set generator for width 3. So how do you random restrict a width 3 read once branching program? We don't really do that. What we show is the following. If you want to construct a hitting set generator for this class, it actually suffices to construct a hitting set generator for read once CNF formulas where some of the clauses are allowed to be parities of variables, right? So this is a new class which I'm going to call CNF with parity. There was nothing known about this class before, but that's only because no one cared about it before us, right? And for this class, we actually get a PRG for CNF with parity. And since a hitting set generator for this class suffices to get a hitting set generator for bit 3, therefore we get a hitting set generator for these things. So the thing you're random restricting is really the CNF with parity. All right, good. Yeah, Rocco? Yeah, so CNF, read once CNF formulas, but in some clauses, instead of the OR of the variables, I'll have the XOR of the variables, right? Feels kind of powerful, but really, how many parities are you going to put in there, right? Each of these is 1, only with probability half. You got an AND at the top, so there can only be log n of these, really. So, I mean, the virtue of this class is not its naturalness. It's that actually by getting a hitting set for these things, you're getting a hitting set for width 3, which is somewhat surprising because if you think about width 3, there are fairly interesting things they can do, like the mod 3 function and so on, right? So how did you just get away with CNF and parities? Okay. No, it's just a reduction saying if you get a hitting set for this, then, you know, so basically here is a width 3 branching program. So here is 0, 1 to the n. This is a set of strings accepted by a width 3 branching program which say has density 1 over n squared. Sitting somewhere in there is the set of strings accepted by a CNF with parity function which has density something like 1 over n to the 100. So if you're able to hit that, then you're also hitting this. Think of it as a lower sandwicher for every. Okay, so if there are, oh, sorry. So why do we care about this small error parameter? Well, really, if you're trying to de-randomize a complexity class, then, you know, epsilon being some small constant is good enough for your purposes. But there are other more specific applications where you do care about the dependence on epsilon. My favorite example is approximate DNF counting, right? Where the goal is to multiplicatively approximate the number of solutions to a DNF formula. Now, a pseudorandom generator usually gives you an additive approximation, but a good enough pseudorandom generator for DNFs can actually be converted into a multiplicative approximation. So this is a result by Karp and Luby from many years back. But the error dependence, if you want a 1 plus epsilon approximation for the DNF, you need to have an epsilon over m error in your PRG, right? So naturally, you start thinking about the case of very small error. Yes, for hybrid arguments. Also, as Raghu pointed out to me just this morning, if you want to have a hitting set generator for width 4, you better be able to hit with 3 programs which have very small accepting probability, because I could have a with 4 program which is just the OR of many identical copies of this with 3 program. All right, so that concludes the long introduction. Now I'll tell you what exactly we do. So basically, I'm going to take some time to really explain how our generator is going to work for the very specific case of the tribes function, right? Because it really contains the main idea. If you understand what it is that works in the case of tribes, it's not easy to do everything beyond that, but you know, it can be done. All right. So let's think about the tribes function now as I defined it before. So you have these m clauses, each of which 2 raised to w. So what I want to do in the first step is to just set the first half of the variables in every clause. Right? So in step 1, I'm going to set first half in each clause. Sorry, I'm saying clause. I'm thinking of a DNF formula, so I should be saying term. This is going to happen a lot. Okay? And what I'd like to understand is, let's denote these bits, the first half the bits in each clause by x. So x is x1 through xw over 2, then x2w plus 1 till, so on and so forth and so on, right? So what is the property I really want out of this clause, right? So I claim that the property I would like is the following. Suppose I sample the other bits uniformly at random. If I sample the rest of the assignment at random, what I'd like to see, let's call the rest of the assignment y. So here is what I want. When I sample the first half from an epsilon bias distribution and the second half from the uniform distribution, and I apply that to f, this expectation is very close to what happens when I sample the first half and the second half from the uniform distribution. Right? Why do I want this? Well, now I can at least say that I've de-randomized the random restriction, and then I can apply this argument iteratively. I've set half the bits in the first step, the next step I'll set half more, and so on and so forth. In log n steps, I've practically set everything, right? At least I've come down to a really small formula, which is very easy to fool, right? Sorry? Oh, yeah, so what am I trying to do in this step? In this step, just imagine that I'm trying to de-randomize. Think of x as a random restriction, which is setting the first half of the bits. Now, rather than setting these bits truly randomly, I want to set them from an epsilon bias distribution, right? What uses? It's the first half of the variables in every clause. So in every term, right? So each of these has w bits feeding into it. I take the first half, I set them randomly. You know, I'm taking a lot of liberties here. I know exactly what variables feed into each gate and so on. But, you know, just as a toy problem, let's try and do this first. Rather than setting these bits uniformly randomly, what happens if I set them from a limited independence distribution? Okay, so here is the statement that I want, right? Is this even true? Why should such a statement be true? The first approach you could try might be something as follows. Well, rather than thinking of setting the first half, thinking of that as your random restriction, think of setting the second half y as another random restriction, also with probability half, right? What would be really nice is if in both of these, we are setting the second half with a truly random restriction. So it would be great if our formula somehow simplifies under this random restriction, and it becomes something like a decision tree, which we know how to fool using epsilon bias. In that case, this statement is just immediate, right? Hit it with a random restriction, you get a decision tree, epsilon bias will fool decision trees. Unfortunately, this is way too optimistic, right? If you take the tribes function, you hit it with a random restriction of probability half, what do you get? Do you get a decision tree? Well, you know, this might be hard to compute on the fly. Hastad's switching lemma says that if you hit it with a random restriction where variables survive with probability 1 over w, then you get a decision tree. With probability half, it's very unlikely, because if it were true, you'd expect that Hastad has proved it already. A more indirect way to see this is that really when you hit this with a random restriction, the clause widths shrink by half. So roughly what you get is a tribes function of width w over 2. This is again something which epsilon bias is not very good at fooling. Okay? So this argument is a little too optimistic. Okay. So, sure. No, you wouldn't get log squared n, because you're setting half the bits in each clause. So the clause width is shrinking by half, right? So I'm hiding something, which is what's happening to the number of clauses. If you really believe that the clause width is shrinking by half, you're actually buying that the number of clauses is shrinking polynomially, because, you know, if you have clause width w over 2 and your bias is reasonable, you cannot have more than 2 to the w over 2 clauses. But, you know, it's easier just to think about the clause width and see that that is decreasing very rapidly. Okay. So the key idea is going to be to look at something which I call the bias function of a restriction. So given a Boolean function f, I'm going to define the bias function over all partial assignments even to this Boolean function. So the bias function of f, which I'll call f bar, is a function from +1, -1, star to the n to 0, 1, where f started off as a function +, -1 to the n to 0, 1. Okay. So f bar for a partial assignment x is defined as just the expectation of the function when I sample the remainder of the bits uniformly. Okay. So if you assign all the bits, it's just the value of the function. If you assign just a few bits, it's the expectation. It's a very reasonable function. Now I claim that what this equation is telling us is that we really only want to fool the bias function of the random restriction. So this is really saying that expectation x in D f bar x minus expectation x in U f bar is small. Okay. And my claim is going to be that this bias function actually simplifies quite considerably under a random restriction, right? That the bias function you get is something that we can actually, when you set half the variables at random, the bias function you get can actually be fooled by epsilon bias spaces. Okay. So I'd like you to be moderately surprised that this statement is true, right? Because what is this bias function really? Each setting of y defines for us a restricted function, which here we argued very eloquently that this is just tribes on w over 2 variables. It's not something that has small L1 norm. Then what did I do here? Well, I just average this over all these tribes-like functions that you get, and what I get at the end of that is not quite something with small L1 norm in itself, but it's something that has good sandwiching approximators with small L1 norm, right? So I find this slightly surprising that I have. So we won't do it by cancellations, right? We look at. I see. So let's go. This is what's coming next. So maybe let's have a look. I mean, I'm also a bit puzzled, I should admit. So maybe you'll tell me what the intuitive explanation is. No. okay, so the one sentence explanation is that you're taking the OR of a bunch of variables. By hitting it with a random restriction, you're keeping the expectation of these variables same, but damping the variance way down. And that is why this resulting function is easy to approximate using loading.
Yeah, but that doesn't explain why half is the right thing.
Half is not the right thing. Any constant would do.
Yeah,
So it shouldn't.
Why a constant?
Yeah, you'll see why a constant though. Will you? We'll see. Yeah, yeah, some constant. Yes, any constant will do. Even a random restriction, we can't prove this of course, but you can set 0.9999 fraction of the bits at a time, and even that ought to work. Okay. So really, the building block here is to look at a single term and understand how its bias function is changing under this random restriction. Right? So let's look at the first term. Right? In this case, f1 x is just the, well, it's the and of x I going from 1 to w. And now what I'm going to do is I'm going to set the second the w over 2 lateral bits uniformly at random. So what happens to this term after that, right? What we are, so okay, what is our experiment now? I'm going to choose yw over 2 plus 1 through yw at random, and think of these x1 through xw over 2 as variables. We are trying to decide what distribution should we sample them from, right? So think of these as formal variables for now. So when I sample these y's at random, what's going to happen? Most likely the clause will just vanish because it's an and one of these variables will be set wrong, right? So with probability 1 by 2 raised to, 1 minus 1 over 2 raised to w over 2, I'll just get the 0 function. With probability 1 by 2 raised to w over 2, I'll get the and function on the first w over 2 variables. Okay. Now, what is the bias function? It is the expectation that I see over a random choice of y. So the bias function f bar 1 is simply, well, most of the time it's 0, and with probability 1 by 2 raised to w over 2, it's the and function. Okay. All right. So what is this now as a function of x's? It's a random variable. Oh, so yeah, I took the expectation. This is the right thing to do. So let's do some computation here, right? With probability 1 by 2 raised to w over 2, this thing will actually be 1, right? And with the rest of the time, it's just going to be 0. So if the distribution of fi under the uniform distribution on x's, if you set x's uniformly at random, you'll get 0 with probability 1 minus 1 by 2 raised to w over 2, and you'll get 1 by 2 raised to w over 2 with probability. So now we can compute out what its expectation is and what its variance is. You'll see that the expectation of f1 bar is just 1 over 2 to the w, right? So what is the expectation? It's like when I set y at random and then I set x at random, what's the probability? It's 1. So it would be very surprising if the expectation was any different than the expectation of the clause itself. But what is the variance of this guy now, right? So what is the variance of f1? Let's do this calculation. f1 bar, yes. f1 is pretty high. With probability 1 over 2 to the w over 2, I claim that I should get this, and with the remaining probability, I get a fairly small deviation. So it's approximately 1 by 2 raised to 3w over 2. So what is really going on here, right? Let's just compare what happened when we replace just half the xi's versus when we replace all the xi's at one shot. In the previous case, what we had is a 0, 1 random variable, which was 0 most of the time with probability 1 minus 1 over 2 to the w, and it was 1 with probability 1 over 2 to the w. A random variable like this has fairly small expectation, 1 over 2 to the w, but its variance is also pretty large. It's also like 1 over 2 to the w. Now what I've done is to replace this variable with this variable fi bar. So this is what fi looks like, f1 looks like under uniform x. This is what f1 bar looks like under uniform x. It is 0 with probability 1 minus 1 by 2 raised to w over 2. When it's non-zero, it's not terribly large either. It takes on the value 1 by 2 raised to w over 2 the rest of the time, right? So I'm not sure what my axes are here, but you get the idea. It, when it's large, it's not very large. The expectation stays the same, but the variance now, instead of being 1 over 2 to the w, has become 1 over 2 to the 1.5 w. And any constant would really have damped down the variance a little. It would have become something smaller than 1 over 2 to the w. Why is this so important? This is important because the number of clauses in my formula is something like 2 raised to w. It's 2 to the w times, it's at most 2 to the w times log of 1 over the bias. So let's just say it's 2 to the w. Now when I sum the variance over all clauses, even that quantity is small. It's going to 0. This is what makes the bias function easy to approximate, right? I'm going to prove that formally now. Okay, any questions about this? Does this satisfy the intuitive explanation, this thing? You just reduce the variance in each coordinate. Okay. So now we've done the computation for each coordinate fi, and we've seen that we've reduced the variance. Now let us see what the bias function of the entire tripes function is going to be, right? So f is just the and of the various fi's, right? And oh yes, good, thank you. I was wondering something was going to happen funny. It's the or of the fi's. So you can expand it out as the product of 1 minus fi, right? So if f of x is, so it's just the product of 1 minus fi x, right? Now what we are doing to this function f is setting half the bits by some distribution that we'll choose, and setting half the bits according to the uniform distribution. We want to understand what the bias function here looks like. Do you have a question? Low. Yeah, but in some sense, Booleanness is very important to kick in, right? So I'm not sure I could, if you just look at the Fourier spectrum, yeah, so short, I'd have to think about it. I'm not sure you can relate it to that. Okay, so now what are we doing? We are setting half the bits here at random. We want to know what is the bias function of f. The bias function of f at x is just the expectation when I set y uniformly at random of f x concatenated with y, right? So this is just going to be the expectation when I choose y uniformly at random of 1 minus fi x concatenated with y. And remember that this is a read once formula, so the various yi's going to the various fi's are all distinct, right? And now, because we are considering y which is under the uniform distribution, we can say that the product of the expectation of the product is the product of expectations. I'll take this expectation inside. What I'll get is the product of 1 minus fi bar x. Okay. So, of course, if there was no y, if we're just doing this under the uniform distribution, then you have this formula just trivial, right? But it kind of holds even when you do partial assignments. Okay. So now I claim that things are looking fairly good for us because you have this product formula which has a very nice shape, right? So what you could do now is to write out each fi, write it out as a mean zero variable. It has certain expectation and expand it about that, right? So I'm going to write it as a product of 1 minus 1 over 2 to the w minus gi bar x, where gi bar is just fi bar minus its expectation. Oh, good. Maybe. No, the expectation is 1 over 2 to the w, right? Okay, fine. But we're trying to fool it, right? So who cares? Okay. So now we have this product, right? And what you could roughly do is to, fi is gi plus 1 by 2 to the w. So I think I want my minus back here. So this is not important, okay? So, but it is in fact minus, right? So now what I can do is pull out this product of 1 minus 2 to the w's. When I take the product of that, that is the true expectation of the function. It becomes the true expectation times the product of 1 minus gi bar divided by something which is very close to 1, and therefore I'm going to ignore. This basically you'd imagine looks like e to the minus the summation of gi bar x, right? What we'd love to do here is to use Taylor's expansion and expand this out as p times 1 minus summation gi bar plus summation gi bar squared, and so on and so forth, right? Now, this expansion is only going to be any good if I can guarantee that gi bar is small a lot of the time, right? And this is exactly what the low variance will buy us, right? Most of the time, this gi bar is going to be a very small quantity. If it's a small quantity, then you can do a good truncation of your Taylor series, right? We are looking, what is the kth term here going to look like? The kth term here is going to be summation gi x raised to k, right? Now, the total variance of summation gi is small as a function of w. It's 1 over some constant like 1.1 raised to w. So if I want the truncation error to be around log n, I should truncate this series around k, which is log n over w, right? And then the Taylor series gives me very small error. And actually, this will work well even when you have epsilon bias, right? Because you have with w terms, you are taking something like log n over w of them. So in total, each of these monomials depends only on log n variables. And one nice property of epsilon bias spaces is that the distribution you see on any log n variables is close to independent, right? So I claim that this truncation will work, and it will work well even under limited independence. So when the width, so sorry, I should stress that this is a very important part of the construction. We are tuning where to truncate it to the width of the tribes function. If w is around log n, we'll truncate it after constantly many terms because already the error has dropped. But what if w is only something like root log n? Then you'll go way out up to degree root log n and truncate it, because that is where the terms become polynomially small, right? So yeah, you're making a very important observation here, which is that the length of the expansion we need to take has to be tuned to the width of the clauses. Okay? which is not so much of a problem in this toy example, but when you want to do general CNFs which have clauses of all kinds of widths floating around, then it's not clear how you're going to make this argument. But I guess the question at this time is, are we kind of convinced that this is at least going to work for the tribes function? I'll kind of hand wave over that. But basically, once you have the sum of the variances small, right, then you expect, okay, let me just, I won't make it precise, but let me try and convince you that most of the time the sum of the GI should be small. Okay. So what do we know about the GIs? We know that expectation of each GI, oh, this is the, hit the, I feel like I'm writing on the wall here. Okay, so we know that the expectation of GIs is 0. What is expectation of GI squared? Oh, yeah, yeah. I knew there was a bracket somewhere there. So expectation of GI squared, we computed it out, is something like 1 by 2 raised to 3w by 2. Right? So what is the expectation of the sum of the GI squared? Well, that's just the sum of the expectations. It's still exponentially small in w. It's something like 1 by 2 raised to w over 2. Now, what do I expect the kth moment of a sum of mean 0 variables to look like, right? I claim that you should expect summation gi raised to k, its expectation, to be of the order of 1 by 2 raised to some constant here, which I'll ignore, times w times k, right? Now, there's some sleight of hand here. You cannot get this just from variance bounds. You need higher moment inequalities on the GIs. I think this is the artifact of this proof technique. The proof I'll actually show you, we do use this quantity, but we do use bounds on the higher moments, but I really think it shouldn't be required, which is why I'm going to gloss over this, right? So assuming this inequality, now most of the time the truncation works well. All you have to worry about is what if this condition doesn't hold, right? But you know, as we'll see when we make this proof rigorous, there are ways to handle that also. Okay. Any questions so far? I'm going to claim this is more or less a proof of how to do tribes. No, nothing here is obvious. But I'm going to show you enough of the proof from which you can construct, you'll see what the bounding polynomials ought to be. Probably, you know, there's some constant there which I didn't write anyway. Yeah. So hang on, firstly, I don't quite buy that you should call anything here inclusion exclusion, right? What we've done is kind of a Taylor expansion about the mean. It is somehow truncation. Well, that's not the approximation in itself. Most of the time that's an approximation. The rest of the time, well, you'll see. You guys are trying to finish a real proof now, and I'm not ready to do that yet. So we do break at some point, right? We will, okay. Yeah, there is a natural break point, so we'll break at that time. Okay. Okay. So why is the case of general DNFs going to be much harder? Well, as we just saw, firstly, clauses are of different sizes, right? So it seems that in this argument, we've tailored the Taylor expansion to the width of the clause, and this, you know, if you don't know the width, then you can't do this. Secondly, this is a slightly bigger problem. You don't know the assignment of variables to clauses. So here, I'm saying that if I assign just a small fraction of the variables at a time, I'm good. But I don't know what variables are in what clause. The best I can do is just choose which variables to assign randomly, and then assign them randomly. And now, you know, you're going to assign a lot of variables in some clauses, very few in some other clauses. You're going to have to deal with all this. Even if you start with a tribes function where everything has the same width, you will mess it up in step 1 when you do random assignments. Right? And finally, a lot of our calculations have been very tailored to, oh, I know this is tribes on width W, I can compute its variance and so on and so forth. So we'd like a more robust statement about this Taylor expansion and so on and so forth, right? Okay. And if you want to do combinatorial rectangles, what are the things that trouble you? Well, each fi is no longer the AND function. So, you know, here it seems like we did things which were very specific to the AND function. We said, oh, if I set the variables the wrong way, then, you know, it just vanishes, and that's why I got my small variance. What if fi is just some function that you know nothing about, right? Okay. So since you guys are craving a formal statement, I'm actually going to tell you our, you know, main theorem in its full glory, right? So this theorem is about fooling any symmetric function of certain kinds of functions. So here is my setup. I have G1 through Gm, which are functions on plus minus 1 to R, right? These have mean 0. They have reasonably small L1 norm. It's less than equal to some t, and the main condition they satisfy, okay, they have some variance. I have a bound on their variance. Expectation gi squared is equal to sigma I squared. Okay. And what I know about them is that the sum of sigma I squared is less than 1. Okay. In fact, I know something stronger. It's quantitatively somewhat small. If I want a final error which is polynomially small in n, I'll assume that I start off with the variance being less than 1 over log n to the 25. Just a technicality. Now, what am I trying? What are these GIs? Well, these GIs are exactly those things. They are mean 0 versions of the bias functions with some scaling factor possibly. Now, what I want to do is to combine these GIs using some symmetric function. So I have P, which is a function from plus minus 1 to the n to the interval 0, 1, let's say. And P is summation Ci Si in G1 through Gn, where the Si's are the various elementary symmetric polynomials, right? Okay. So I take some nice functions, I combine them in a symmetric manner. I'm assuming that P is bounded. I'll also assume that the coefficients are at most 1 in absolute value. I mean, the only function the only P I ever consider is either the OR function or the AND function, but it doesn't hurt to prove a more general statement. They are on disjoint sets of variables. Thank you very much. Okay, so let me write this here. So what is the conclusion? P is, wait, I haven't written a statement of the theorem. Oh, W is the width of the, oh, sorry, I'll bring W into the picture. You know, I'm just giving you a full-blown, yeah, so W is a parameter which controls all these things. The L1 norm will be bounded by exponential in W. This guy will be smaller than 1 over something like 2.1 to the W and so on. I'll talk about that. I'm just giving you a general statement. Then P is delta fooled by epsilon bias for epsilon, which is delta raised to some constant C1 divided by mt raised to some exponent k. What is this exponent k? It is something like log 1 over delta divided by log of 1 over summation sigma I squared. It's quite a mouthful, right? There's a whole lot of parameters floating around. But basically it says if I take functions on disjoint variables which have small variance, I combine them in some symmetric way, these kinds of functions are easy to fool, right? What I really want is this epsilon should be just something like delta to the 100. If I want to delta fool my class of functions, then I can just take epsilon to be really small and I'm done. And if we introduce the parameter w, then actually this will be the case.
But so the exponent ci here is not related to the coefficient.
Oh God, no. Let's call it.
All right.
What would you like? A1, B1, A for Ankur. Yeah. Yeah.
The sum of sigma I squared and this
You really want a full formal statement.
you want to sum it over all G1 to Gn.
Yeah. The total variance needs to be small, right? The total variance. Hang on. Yeah, let's set parameters here. So there's really going to be only, I'm going to collapse everything now to one parameter, w, which is the width of each gi. How many variables does gi depend on, okay? So what we are going to be interested in is situations where the number of terms is something like 2 to the w. This will always be the case for us. The summation of sigma I squared needs to be, I still want it to be small, exponentially small in w, right? I want this guy to be something like 1.1 to the w. So this will require that each sigma I squared is less than something like 1 over 2.1 to the w, which is exactly what we got in the DNF case, where we got 8 over 3 in the denominator, right? So now this takes care of this condition that the summation sigma I squared is small. Uh-huh. Yes. Yeah, sorry. So ignore why this condition is here. I need the variance. What I really want is that the variance should be exponentially small in this parameter w, so that I can expand out to log 1 over delta divided by w terms. Okay. Sorry, is this condition confusing you? Oh, okay. So what this says, so yeah, this lemma will only apply it as long as the width is at least log n, right? So if the width is at least log n, once I have 2.1 to the w, this condition gets automatically satisfied. Yeah, so once the width becomes log n, I have other ways of dealing with it, so I won't really. So you know, if this is a technical issue, it shouldn't bother us. So if you're happier with this, let's just say that sigma squared is less than 1 with a caveat that it's not really true. I want the variance, the total variance, to be exponentially small in the parameter w. Okay. Okay, yeah, each of them is, you know, they are on distinct variables. So yeah, each gi is plus minus 1 raised to its set of w variables onto r. Okay. So let's go back here, right? So if the total variance is exponentially small in w, and imagine that delta is 1 over polynomial in n, then in this case, k really is something like log n divided by w, right? So now this mt to the k, what happens here? This is some exponential in w raised to, well, this is actually log 1 over delta divided by w. So this is some exponential in w raised to the power log 1 over delta over w, so it is in fact polynomial in 1 over delta, right? So in the case where we care about, yeah, t will also be like t to the 2 to the w, because it's a function on w variables, how much L1 norm can it have, right? Okay, so this is theorem number 1 which we need. This hasn't addressed our concern really about what happens when there are many different widths involved in our CNF formula, right? Then, you know, this again seemed to be talking about clauses which all have equal width or nearly the same width, right? So to handle this business of clauses with widely differing widths, we also prove some kind of XOR lemma for epsilon bias spaces. So the XOR lemma basically says that when you have a read once function, it's okay to slice it up into different parts and fool each of these using epsilon bias. Then you can put it together and claim that the overall function will also be fooled by epsilon bias. Yeah, well, log n or something like that. So I'll write down a precise statement here. Sorry, Mark, what is it? Yeah, that's there's many there. Well, actually, there's two there. This is one of them. So here's a precise statement. Let f1 through fk be functions from plus minus 1 to 0, 1. Again, they are on disjoint inputs, right? On disjoint inputs. So this is best stated in terms on sandwich, in terms of sandwiching polynomials. So let's say they have delta approximating, sandwich approximating polynomials of L1 norm t, each one of them. Yeah. So each one of them individually is fooled by epsilon bias. Right? Now I'm going to combine these functions in some way, and I want to argue that I can fool this combination using some slightly stronger epsilon bias space. Right? So I'm going to combine them using a combining function h 0 1 raised to k to 0 1. Right? So the final function I'm interested in is little h, which is capital H applied to f1 through fk. No, but if you want, you can have it. Then the claim is h has 2 to the k times delta sandwiching approximations of L1 norm 2 to the k times t to the k. Right? So this is why you want to keep k small. You aren't paying much in terms of error, but basically you're doing some kind of product construction, and so your L1 norm goes like t to the k. Right? So as Mark says, if k is like log n, t is at poly n, this is still manageable. But you shouldn't do lazy things like make a separate bucket for each and every width and get k equals log n. Okay, let's prove this, or at least see how the proof should go. Right? So we are proving this for general functions h of f1 through fk. That's only because we can get it with no additional effort, right? Let's just construct sandwiching. Sorry? Yes, very good. Okay, let's prove it for monomials. So I have f1 times fk. How do I get an upper sandwiching polynomial for it? I have upper and lower sandwiching polynomials for each and every one of them, remember. Use the product, right? So f1 upper to fk upper is greater than this. How do I get a lower sandwiching polynomial for it? No. So what is the problem? Wait, maybe what you said is actually right. Oh god. So the worst audience ever. Okay, what I would like to try, and what some intelligent people have thought would work, is to take the product of lower sandwiching polynomials. This is not going to work because the upper sandwiching polynomial is always positive, the lower sandwiching thing could be negative, and it seems that negative times negative is sometimes positive, right? So you won't get a lower sandwiching polynomial that way. But let's do the following. Let's consider all monomials and just try and upper sandwich each and every one of them. Let's consider 1 minus f1 times f2 and so on and so forth. I can get an upper sandwicher for this one too, because 1 minus f1 lower is upper sandwiching for this. Now what is this statement really telling me? It's kind of telling me that if I look at the joint distribution of the fi's, then no value is taken too often. Right? So if these FIs are actually Boolean functions, then this is exactly what it's telling you, that it doesn't take the all ones value too often, it doesn't take any other value too often. So of course the distribution overall is correct with a fudge factor of 2 raised to k times delta. You can actually convert this into a statement about polynomials like Avi just did. Okay? All right, this is a really useful lemma, I should point out. And you know, things like this fact I was saying, that on log n variables the distribution is near independent. If you so wished, you could see it as a consequence of this, because you know there t is just 1, right? But okay. So now when we come back, I'm going to show you a sketch of the proof of the main theorem, and after that we'll just apply it to a bunch of things. And yeah. Okay. How long a break do we? Oh, it's up to me. I'll never come back. Okay, well, it's 43. Let's say 48. Let me just firm up this discussion, because I realized maybe it wasn't as clear as it should have been. So what we are observing is that constructing upper sandwiching polynomials for this particular monomial and for is quite easy. If you also consider the monomial 1 minus f1 f2 times fk, then again constructing upper sandwiching polynomials for this is easy. Now, all these monomials are related by the following relation, that if I sum all of these monomials where I take both possible orientations for each variable, then what am I summing? I'm summing to 1, yeah? So this is why you get lower sandwiching polynomials as well. This is essentially what Avi was saying. Okay, so let's go back to our main theorem, right? Why is this theorem true? So I might as well, okay, I'll use this now. No, I'm going to use this now. I want to hide the proof. It's not going to be pretty, so. Okay. So what have we here? We have this summation of CIs, right? And we want to prove that under certain nice conditions, this is easy to approximate, right? We can either construct sandwiching approximations for it, or we can prove that there are low degree polynomials which approximate it well under any epsilon bias distribution. These two are equivalent statements. I prefer going by saying that epsilon bias will actually fool this function. Right? So what is P? It is summation Ci Si in G1 through Gn. Okay. And what do we know about these GIs? We know that they satisfy fairly good moment bounds. Okay. So let's look at how these various SIs ought to behave under the uniform distribution. Right? Yeah. No, I intentionally ignored them in the hope that nobody will point it out. Anyway, by the end of today, they won't be necessary. So, anyway, so computing the expectation of the kth symmetric polynomial here under the uniform distribution. Okay, I need some notation here, right? Let's call this quantity sigma squared, the total variance, which is something which is exponentially small in W. Now, these elementary symmetric polynomials are remarkably well behaved. The kth moment behaves something like sigma raised to k divided by k factorial, right? So, under the uniform distribution, this series of terms, it's really dipping very quickly. You can truncate it at k, which is what you want, log n over w, you'll get an excellent approximation. Is this statement true also for epsilon bias distributions? Right? So I claim that this is just not clear, because epsilon bias distributions, we only know that they fool polynomials with small L1 norm. And once k gets really large, the L1 norm of these polynomials is enormous. So a priori, it's not obvious that you're going to get this kind of a distribution even with epsilon bias, right? But what we're going to say is that there is some kind of causal connection between these various symmetric polynomials being small. If S1 and S2 are small, then that's it. The whole series will actually fall this way, right? So let me write down the formal statement here. Okay, and fooling S1 and S2, epsilon bias spaces can do this very well. That it should behave like the Taylor expansion, I guess. I don't know. It seems
very related to sort of a,
seems like the
waving to the higher moment bounds too, right?
yeah. So the nice thing about this S1 and Sk is that actually to bound these guys, you don't need higher moment bounds. That's one of the things, one of the reasons for doing it this way rather than going to the Taylor series. This statement I said is just true if the variances are, they have to be independent, but only the variances need to be small. Okay, so here is the lemma. If the summation of zi's is small, this is S1 in absolute value, and if summation of zi squared is small, like mu squared, then I claim that the kth symmetric polynomial in the z's can be bounded by mu to the k. It's slightly different from the statement I promised you, which is if S1 and S2 are small, then everything that follows is small. But really, these are more or less equivalent, as we'll see, because S2 is really this thing squared minus this thing. Okay, so I'm going to show you the proof of this. I mean, firstly, it's possible this is known in the literature before. We haven't found it. If you've seen it somewhere, then do let me know. But at the same time, I'm going to show you what's a very simple proof of it. Okay. So rather than bounding the symmetric polynomials directly, we'll first bound the power sums. The power sums are basically the polynomials ek z1 through zm, which is simply summation of zi raised to k, the sum of the kth powers, right? Now once I have a bound, they are just real numbers. So yeah, this lemma is just about this. If the sum of these guys is small, then this claim is true. Yes, yes, yes. M doesn't come up. M doesn't, and that's what we want, right? Like here, the M got eaten up by the small variance. We said the total variance of these things is something exponentially small in W. So now, you know, I want the k term to behave like something raised this 2 by W to the k. I don't want M to show up there anywhere. I don't. Maybe you could. Okay. So once I have a bound on the sum of squares, then I get a bound on ek pretty easily, right? These are just the LP. It's a good question, and there is a good reason to hope for a k factorial. Let's talk about this later. Oh, sorry.
No, but I mean, you can't, right? I mean, what if Z1 is...
Think about it. And the rest are all 0. That's the nice thing about SK.
Oh, I see.
It's not sensitive to a few large values, and this is why we are dealing with the SKs. Yeah. Okay. So firstly, I claim that since I have this bound on the sum of the squares, I can easily bound Ek as the absolute value of Ek. It's less than the sum of the absolute values of Zi raised to k. It's less than equal to mu to the k. Right? This is just the LP norm inequalities. Okay. Now the relation between these power sums and the elementary symmetric polynomials, it's a classical formula called the Newton-Girard identities. Well, I think, yeah, he proved it. I mean, who do you name theorems after? The last person to prove it, right? This is historical tradition. Okay, so the Newton-Girard identities, the simplest case is how do you bound S2 once I have a bound on these two, right? Well, let us take the sum of the zi's and square them, and then I'll get all these cross products and I'll get square terms which I have to cancel out. So it is summation zi squared minus the sum of the zi squared, and I have to divide by half, right? So here immediately I would get S2 is less than mu squared. So this immediately gives me that S2 is less than equal to mu squared, right? Because this quantity is bounded by mu squared, this quantity is bounded by mu squared, and I can divide by 2. Okay. In general, Sk is 1 over k times Sk minus 1 times E1 minus Sk minus 2 times E2, so on and so forth. So what do? You take Sk minus 1, you multiply it by E1, which is just the sum. You get all the terms you want, you actually get them k times, but you also get these squares, which you now cancel out using this. This creates cubes, and you keep going, and finally it ends, right? Now, I want to bound the absolute value of this. This is expressing it as an average of k other quantities, each of which I can already bound in absolute value by mu to the k, so I'm done. Okay. All right. So what have I proved to you so far? I've proved to you that the truncation works very well if just z1, if essentially the first two elementary symmetric polynomials are small. And this is very good for us because the first two elementary symmetric polynomials, they have very small norm, right? So you don't need to worry about the SKs having huge L1 norm. Okay. So at this point now, the proof is going to transition to a lot of hand waving, right? So I mean, this is the main idea really. The rest of it is more or less technical detail. Right? So I define a good event G, which is the event that summation of gi's is less than equal to mu, and summation of gi squared is less than equal to mu squared, right? And mu is going to be something like 1 over 1.1 raised to w, and this is going to be something like 1 over 1.1 raised to 2w. Now, if this event happens, then I am in great shape because I can truncate and I'll get very small error, right? So now I just need to worry about what is the probability of this event, right? Because if I just use Markov's inequality on gi's, I'm not getting an inverse polynomial probability bound. I'm only getting a bound like 1.1 raised to w. So what do? Well, you do the standard thing. You look at the high moment of this guy, look at the kth moment of this guy, right? And here is where things get a bit nasty because now you actually need kth moments. You actually need kth moment bounds for each gi, right? The right way to do this ought to be to just to just argue about the SKs directly, right? You say that maybe if SK and SK plus 1 are small, then everything which follows is very tiny. And then you'd get your probability bound very nicely, you'd get your tail bound. The problem is I don't know an analog of this statement for SK and SK plus 1. Okay, so this is all I'm going to show you about the proof of the main theorem. Is anyone still unsatisfied? You can talk to Raghu later after I'm done. Tomorrow, yeah. Yeah, good. Day after, actually. Okay. So at this point, we have our main tools, which is this theorem, which talks about fooling symmetric polynomials under fairly general conditions. And then we have this second part, which is this XOR lemma. And now I'm going to actually, I haven't told you anything about what my generators look like. I'll actually tell you how to put these together and get generators for CNFs and rectangles. Okay. So not uniform, but within a small w to 1.1 w. Yeah. Yeah. Oh, this is hard work. Sorry? You must have some powerful speakers. Okay. What is the generator for CNFs going to look like? Well, I'm going to iteratively apply the following kind of random restriction. For each variable x1 through xm, I have no idea, right? I have variables x1 through xm. It is actually, wow, yeah, okay, fine. Okay, so combinatorial rectangles. Okay, so I have this rectangle here where each coordinate is a function fi from plus minus 1 to the w to 0, 1. So I have these m rectangles and I'm taking the and. Okay. So what I'd like to do is to go on hitting these rectangles with random restrictions of probability, say 1/2. So what is the notion of random restriction for a combinatorial rectangle? Right. So I want the universe size to shrink from 2 to the w to something like 2 to the w over 2. And I'll do it in the most obvious way possible. I'll just subsample a set of points here of cardinality 2 to the w over 2. And I'll subsample with repetition, right? I'll put these points into a new coordinate, which is now a new function, let's call it hi, from 2 to the plus minus 1 to the w over 2 to 0, 1. I'll do this independently. Imagine doing this independently for every coordinate. Subsample a set of points in the universe, this defines your new rectangle. Okay. So this is some reasonable notion of how you restrict a combinatorial rectangle. I claim that you can de-randomize this. Just do the sampling using an epsilon bias string instead of using truly random bits. No, I'm sampling with repetition. I'm actually using much more. I sample, so what do I do here? Let me code the restriction up and you'll see what exactly is going on. For each coordinate, I choose a matrix of size 2 to the v times w, where v is, we have taken v to be w over 2, right? So let me just say it's 2 to the w over 2 times w. Each row here is going to be a point sampled with repetition, right? And now I do this for each and every coordinate independently, initially, let's say. This defines my new combinatorial rectangle, right? This is now a combinatorial rectangle on, m coordinates, each of which only w over 2. Sorry. It's an and of these functions. Yeah. Each function takes w bits, right? So think of this as a reduction from. The rectangle is the and of all these things. It's a subset of size 2 to the w. Some points are 1, some points are 0, right? What I did now is to subsample with repetition a set of these many coordinates. I make that my new rectangle, right? For each coordinate, I subsample the universe. Sorry, I made it a new, my coordinates look like rectangles. I make each of these a new coordinate. The new rectangle is the and of all these coordinates, right?
The new function is defined. You take a subset of this set of w. You're just shrinking the domain.
I'm just shrinking the domain.
W, you're looking at the restriction of fi to a smaller set.
Yeah.
So isn't this like fixing?
It is like it, but no, I haven't. I mean, these are very. You're talking about subcubes. I'm talking about subsets sampled with repetition. There is much more randomness here. Maybe that would work, but why? I'm finally going to just use an epsilon bias string, so might as well hit it with all the randomness that I need. Okay, sorry. I'm sorry this was unclear. This is actually not a very complicated thing. We just subsample a smaller subset of the universe with repetition. That defines my new rectangle. Now the width has shrunk by a factor of 2. You go on doing this, and in log of w, which is roughly log in steps, you'll reach something very simple which you can prove. Okay? And now I claim that this whole matrix which I need in order to define this restriction can be chosen according to an epsilon bias space. Okay? So, here without proofs, let me just tell you what it is that we needed, right? Look at each coordinate, look at the ith coordinate. Now, I've chosen these strings x1 till x2 to the w over 2. What is the function of these things that matters to us? Well, it's just the function, the coordinate function fi averaged over all these points. Fi bar, the bias function, will turn out to be simply 1 by 2 raised to w over 2 times the summation of the fi applied to these strings xi j. Right? This is clearly a variable that has very good concentration. I am sampling 2 to the v times from this universe. I expect the mean to be correct. I expect the variance to be very small, right? Which is why you can derandomize it using our construction. Okay, is the generator and how it should be analyzed clear? So what is the, how does this recursion bottom out? Let me just say a word. Finally, the rectangles will shrink to width something like log n. Then you can write this as a DNF of width log n. And for such kinds of DNFs with small width, you have very good pseudorandom generators with seed length nearly log n. I guess this comes from recent work that Raghu and I did with Omer. Or earlier even? Maybe. Sorry. Yeah. Yeah. Yeah, so because of these moment conditions, currently the constant is half, which I'm hiding. If you get rid of this, then you can do it more, but you can only shrink it a constant factor at a time. Right? This, I won't get into this right now. Okay, so we're done with rectangles. Let's do CNFs. So I guess I can erase this. Conceivable, but there's at least 2 log n's there, and maybe I'd have to think about it. You know, I don't see. In the CNF case, right? In the combinatorial rectangles case, you actually use the XOR lemma, but you only break it into 2 buckets. Now, nobody's going to ask me why this is the case, but yeah. But that might, but see, no, but Raghu, that, if you gain back the k factorial, that might go away. Okay. So now CNFs, right? So I have x1 through xm, xn through xn, which are my random variables. I don't know how they're going into clauses. I'm going to sample a random restriction in the following way. I sample a new string y1 through yn, you know, which for each bit tells me, do I want to restrict this coordinate or not? Then I sample z1 through zn, which says, if you restrict it, here's the value to put. So what we're finally plugging in every coordinate is the following kind of small decision tree. You look at yi. If it says +1, then you plug in zi. Otherwise, you leave xi untouched. Okay. Yeah, so now, yeah, sure. This is just one step where you restrict about half the variables, and you know, you go on doing this again and again. Now it's a bit subtle to argue that the width actually shrinks, because there will be clauses that you just don't hit. But you can argue that except for a few clauses, you know, which don't bother us too much, things do behave as you expect, that the width and hence the number of clauses is shrinking, and in log n steps, I'm left with a very simple CNF formula which I can fool using epsilon bias. Okay. Okay, that is the one thing. The other thing is that you need to do this bucketing now, because I only have a theorem which applies to clauses which are of nearly equal width. So basically, I'll take all clauses which are of width between w and 1.1 w, I'll sandwich them, then I'll move to the next bucket, so on and so forth. So there are log n buckets. This is where another log n will come from. Okay, sorry. Yeah, let me finish this, right? So here, these are the random restriction bits, right? So we'll do our usual computation where we'll say, okay, what do I expect from my y's and z's? What is the expectation over a truly random choice of xi, right? You'll do this for every clause. And I'm not going to do this calculation, it's too late in the day for that. But basically what happens is, most likely after a random restriction, the clause goes away. If it does not go away, it will probably shrink down in size. You'll get a smaller clause, right? So if you do the variance computation, then you'll get exactly what we got before, which is that fi bar of these, now I've changed notation, y and z are my restriction bits. You'll see that it's something like 3 over 8 raised to w. It's an entirely straightforward calculation. You can actually write down the exact expression for the monomial that you're trying to fool and compute out its variance, right? The important thing is that 3/8 to the w is less than 2 to the w. Oh, sorry, yeah, this is the variance. So, yeah, so the variance of this function fi bar is this. Yes, that's all I need, and I'll get that with any constant random restriction. Okay, so this tells you more or less how the case of CNFs is done. Now, in the last 5 or 10 minutes, oh, sorry. So, okay, what's going on in this thing, right? The y's and z's are my restriction bits. I argued that the resulting formula has low variance, so actually I can do this restriction epsilon biased, right? Both the y's and the z's are epsilon biased. Now what do I get? I get a smaller formula. I restrict it again, but with epsilon biased bits. I repeat this log n times, and then I'm done. And then at the end, I'll just plug in an epsilon biased string for everything. Okay. No, I think the independence across the various epsilon biased strings is very important, right? Because epsilon bias doesn't fool these. So the whole theme is, yeah, these are independent epsilon bias strings across iterations, and that independence seems to buy you a lot, right? So I guess this is a theme, that epsilon bias strings themselves may not be very powerful, but it seems like you can combine them in simple ways and do very powerful things.
So this for epsilon bias, when it fools the function, you have this nice, there's a nice characterization in terms of the Fourier spectrum.
Right.
Is there a way, just purely based on the Fourier spectrum, that you can think about when, chaining together, like is there some sort of,
No, I mean,
no?
and I don't know of any, and I'm very glad there isn't, because otherwise you'll be only able to fool the class of functions where you completely understand the Fourier spectrum, and even Rocco doesn't understand the Fourier spectrum of these things. Yeah, so my answer is, I'm glad that so far it seems you can't have a nice clean characterization, so you could try and do. I see. Right. Okay. Now I'm going to change gears completely and talk about the hitting set generator for bit 3, right? How do you reduce this to arguing about a nice class like CNF with some parities, right? And I don't have time to do a formal proof here, so I'm just going to tell you the outline of how the proof goes, like everything else that came before this actually. Okay. In the first step, so what is a bit 3 branching program? So I have 3 layers, and so I have states, right, which have out arrows on 0, marked 0 and 1. I still don't have enough time. I think eating lunch is a better use of those minutes than looking at the proof. Okay. First thing I'm going to do, so this state up here is accept, this state down here is reject, right? First thing I'm going to do is that in each layer, so I'm assuming a lot of preliminaries about these things, like, you know, edges go from layer I to layer I plus 1 and so on and so forth. First thing I'll do is to sort each layer by probability of acceptance, right? So the probability of acceptance, it goes something like this, right? The second thing which is true is that the probability of acceptance also goes like this. Why is this true? This is true because the acceptance probability of this state is the average of the acceptance probabilities of its two successors, right? So this guy here is the average of some two states in this layer, and this is the max in this layer, so it has to be lower. Okay. So a width 3 with sudden death is one where the lower layer is just all reject states. If you ever hit the lower layer, you're rejected. As a first step, we'll say that it suffices to construct a pseudo-random generator for these guys, width 3 with sudden death. So, sorry, hitting set. Now onwards, when I say pseudo-random generator, I really mean hitting set. Okay. Okay. So we're going to assume that this initially has acceptance probability, at least epsilon, right? So what should I try to do? I should try and take these states which already have very small acceptance probability and turn those into reject states, right? And here is how you actually do it. Look for the first state in your program where the acceptance probability is less than epsilon over 2. Right? Let's say it happens here. Until this point, I really don't care where in the branching program I reach, right? So suppose this happens at the kth layer, then really I don't care about the first k minus 1 bits. I could set them to all zeros, right? Of course, I have to guess this k so that I can set them to zeros, but that's fine. So I walk along the all zero string, I get somewhere in this program. In the worst case, I land up in the bottom state, since this has the minimum probability of acceptance. But this probability of acceptance is greater than epsilon over 2, right? Okay. Now we'll wake up and try and do something intelligent. So starting from here, you have epsilon over 2 chance of getting to accept, which means that you have at least epsilon over 2 chance of getting to the top state, right? And maybe your chances are maximized somewhere around this layer, where you have a probability of at least epsilon over 2 divided by n of getting here for the first time. Let me repeat that. With probability epsilon over 2, you get to the top layer at some point. So there is a point here, which is the first point you reach in the top layer with probability epsilon over 2 to the n. Let's take everything that occurred between, so this was k1, this was k2. Everything here becomes a reject, right? Because, you know, the strings which reach here for the first time, they never visit these states. So, you know, we don't harm these strings in any way by turning these into reject states. Okay. So far, so good. Now, here onwards, we'd like to turn something else into reject states. And what is this something else going to be? It's now going to be things in the bottom layer, right? This I'm going to turn into reject states. Okay, let's see. So what happens to my probability of acceptance when I do this? Each of these states have probability less than epsilon over 2 of reaching an accept. This state up here is a fairly good state. The probability of reaching accept from here is at least epsilon. Why? Because it's epsilon at the very beginning, and we argue that the upper layer is decreasing like this. So this is a state which has an acceptance probability of at least epsilon. What I did is I took a bunch of states which have epsilon over 2 or less as their acceptance probability. I turned them into reject states. You can show that this does not affect the acceptance probability here too much. It at worst will become epsilon over 2, right? The idea is, since you have such a good chance of accepting starting from here, it's very unlikely that you'll see any of these shoddy states while walking through the program. So this now defines my new branching program with sudden death, right? Because there are only 2 active states really in any layer. The next state is a reject state. Yes. In the mod 3 sum being 0, you'll get to the very, your probability of, or 2 before the last, who knows? Yeah. Yeah. So you're very happy. That's why things like mod 3 are really, they get eliminated in this step. Okay. Now we have width 3 with sudden death. And from here, I'm going to go to the intersection of with 2 branching programs. Are you talking about this talk now? Okay. So now I have this bottom layer which is completely reject states, right? If you go there, you're dead. I have these top 2 layers. I'm now going to arrange these top 2 layers differently. I'll sort them by the probability that an accepting string visits the state. Okay? So there are 2 other layers here. Now just consider the uniform distribution over accepting strings, right? They pass through this layer at some point. Either they pass to this state or they pass to that state. And finally, they get to accept. Now the trouble is, some of these states have arrows. We are trying to get this to look like a width 2 branching program. And the trouble is, some states insist on having arrows to this reject layer at the bottom. This we don't like. What we'd really like to do is to take these and make these reject states. If you have an arrow, if you have friends down here, then you might as well become a reject state as well. This is what we'd like. This will not work because in some layers, there will be both states having arrows down. This could happen, and then you'll just end up rejecting everything, right? So basically what we show is that you can do this for states which are visited with sufficiently small probability, less than 1/10. Okay? And now we are just left with a few states which are quite likely to be visited, but there turn out to not be too many of them. There is only log n many of these states. So for these, you can basically guess a good setting of bits, right? So, okay, so. No. So, okay, I probably should define these things a bit carefully. So define bad states, right, which have an edge to a reject state. Yeah, no. Break them into the big bad ones and the small bad ones. A big bad one has a probability greater than something like 4/5 of being visited by an accepting string. These things have a probability something less than 1/5 of being visited by an accepting computation. These ones, I claim, you can turn them into reject states. It doesn't harm you much. What to do about these? Well, really, there shouldn't be a lot of states which could take you to reject, which you're visiting if you are an accepting configuration, because at every such state, there's half a chance you die and you don't get to accept. If you visit too many such states, then the chances of accepting become very small, right? So the number of states, the number of sets here is something, the number of, states here is something like log n. And log n variables, when you're dealing with epsilon bias, are never a problem. You can just assume that these bits will come out right. I'll gloss over this part even more than I'm glossing over everything else. Okay? But once you've done this, in essence, you've turned it into a width 2 branching program, because every state that has, you've turned it into an intersection of width 2 branching programs, because every state that had an edge to a reject state, you've basically converted this into a reject state of its own, right? So now my program looks something like this. I'm going to ignore these log n bad states, which we took care of by some other way. We've taken this program and made a bunch of things here into reject states. Now, how can you reach accept starting from the start state? Well, you have to reach this state. From here, you have to reach this state. From here, you have to reach this state, and so on. So each of these is a width 2 branching program, and it is just an intersection of width 2 branching programs, right? So now at least you've seen how width 3 reduces to width 2. Now we need to do some more work to get to CNF of parities. This kind of relies on, so the last step is from width 2 to CNF of parity. An intersection of width 2 to CNF of parity, but basically you're saying just to hit a width 2 program, you need to just hit CNF with parity. Okay. So this relies on this nice characterization of width 2 programs due to Sachs and Zuckerman. So basically what they said is that every width 2 program, in essence, it looks like a simple decision list, where what you do is something like this. You read x1. If it comes out some way, then you compute some parity function. If it comes out the wrong way, well, then you read x2. And now you read some, if it comes out one way, you'll compute some other parity function, and so on and so forth. Right? These parity functions here could be the constant parity function, but you know, these sets actually keep on growing in size. Once they are non-zero, they only get larger. Okay? So now I'm going to do one of two things. I'm going to look at this. I'm going to look at a decision list for this width 2 branching program. If the decision list looks like this, there's x1, there is x2, and there is, if there is a lot of ones at the top, if there's a long run of ones, or if there are any ones really, I'm going to just approximate this by the OR of these variables, right? Here, if the OR of these variables is 1, the output is 1. Otherwise, I have to compute some function. I'm not going to do that. I'm going to make this 0. So now it's simply an OR of variables. And basically, I'm getting most of the accepting configurations anyway. What if there's no 1 up here, right? Well, then it has to be either a 0 or a parity function. For those things, what I'll do is, oops. So I have x1, and then I have some parity function here. I'm just going to replace this by this thing, x1 and this parity. Right? So this is kind of lossy. I'm just getting some small fraction of the total number of strings that this branching program accepts. But notice that this has a rather high probability of rejection, something like 1/4. So there are very few of these, so I can afford to be careless with these things. Okay? And that's it. Yeah. That is fairly, yeah, it's pretty generic. To width W, no, from width W, you'll get to width W minus 1. I think you'll get a program where at various points the width kind of shrinks, right? Sorry, so the first reduction to sudden death, this works for all depths, right? Right, for all widths. The next step, which is intersections of width 2, this does not work for all widths, right? Because I can do this modification. I think all I get is like, you know, so there's, maybe I'll get a reject state here, but there's too many other states, so you know, it's not. Okay, so I should think about this, but yeah, there are things, the first step certainly works for all widths, the second step, parts of it work for all widths, and the last step is very specific to width 2. Yes, yes, it's not. Yeah. I think Ita-Vigdersen pretty much is the first one I'm aware of, where you hit it with a random restriction. So I think what's new here is that we are only trying these very mild random restrictions, which don't simplify your function much, but we're saying they do interesting things with the bias function. Right? Yeah, that as far as I'm aware. I think this is. So maybe, I guess, did we learn something new about read one's DNFs by doing this? I think so, that
Yeah.
this bias function simplifies in this way. I think it's something new. This might even be true about all DNFs, not just read ones.
Learning it again. What you said here.
Yeah, yeah. I mean,
That's
oh, so the newness of the tool, you need to know the literature way better than me to assess how new this tool is. I think, as Avi says,
variance, I mean, the use of this variance is something that's very different from any compliance.
exactly, yeah.
This is the new. And that was my question.
Okay.
And
good.
that, yeah, this is to me like.
I wanted to make this point that maybe it's telling us something interesting about DNFs that we didn't know before, which we only managed to prove in the read ones case. Who knows? Maybe this generator works for all DNFs.
Or also maybe it works for depth 3 read one. We also don't know.
Yeah, yeah. Oh, what? Depth 3 read ones. Oh, okay. Yeah.
Yeah, the last one.
Yeah, yeah. Yeah, sorry, Zed. Well, we're doing read ones, right? So you have to be very careful about what circuit level bounds you want to claim. What we do get is some kind of proof. Well, again, yeah, you could think of this as a different way to prove the switching lemma, but it's really a cheat because the switching lemma is very easy for read ones anyway. I think we've gotten what you could get out of this. This is perhaps the most interesting application. Sorry, there was a question there?